So yung pressure enthalpy diagram that we've discussed for water, meron din actually siyang counterpart for each type of refrigerant. And in which case, obviously, it's the same na you have pressure and enthalpy on either axis. And ang mahalaga dito is yung buong refrigeration cycle ay kaya nating i-drawing as a closed shape doon sa pressure enthalpy chart. Parang visual natin ito para makita yung evaporation, compression, condensation, and expansion. And it also helps us in solving problems, no? Kasi kapag may hinahanap kang point, like let's say the enthalpy of something, the temperature of something, um, makikita mo siya doon sa chart mismo pag pinlot mo siya. So this is an example of a pressure enthalpy diagram for Freon 12 refrigerant. So as you can see, meron din siya nung curve dito. So obviously that means that this is the vapor liquid mixture area. Then dito yung parang critical point niya. So this is the saturated liquid curve, and here is your saturated vapor curve. All points here means you have superheated refrigerant, and all points here mean you have subcooled refrigerant. On the x-axis you have the enthalpy, and on the y-axis you have the pressure. Okay, so as you can see here, nakikita natin dito yung different na phases, no? So when you have expansion, it's a vertical line downwards where there is a decrease in pressure without change in temperature or enthalpy. Okay, and in the evaporation process, you would have a increase in enthalpy. Then in your compression, you usually have the constant entropy curves going towards the superheated region. And ito yun. And in your condensation, you have a decrease in enthalpy. If it's saturated vapor to saturated liquid, there is no change in temperature. Otherwise, meron, no? And then you repeat the process again. So you have an almost rectangular profile except for compression na you follow the constant entropy curve. Okay. In the next slide, we'll see the whole picture of it now. So I want you to take note of this. So in the subcooled region, the horizontal lines are constant. The vertical lines rather indicate constant temperature. On the other hand, in the vapor liquid mixture region, horizontal lines are constant pressure and constant temperature lines. On the other hand, sa superheated region naman, yung constant temperature mo are represented by curves. So, bakit po mahalaga ito, no? Kasi we have to understand how this topographic map of sorts works, no? And then, of course, you have constant entropy curves for your compression. So, kailangan kasi natin yung mga tabular values na ito para ma-solve yung mga problems natin on refrigeration. Okay, so what happens here is, let's say from A to B, which is yung compression mo. So, that increases your constant entropy process that increases the temperature as well as the pressure of your gas. Then as you go to the condensation phase, as you transfer heat from the refrigerant to the surroundings. So, ayan yung ating curve. So you have, in this case, decrease in temperature, then constant temperature, all the way constant pressure po yung phase na ito. Then habang nag-expansion ka, there's a net drop in pressure. Okay. but no change in enthalpy. So walang energy transfer na nagaganap. And then as you evaporate the gas, evaporate the gas, you have in this case no increase in pressure, but an increase in enthalpy and no increase in temperature as well. Okay, and the cycle repeats itself. So take note that we have three enthalpy values of importance. These are either from the table, calculated based on the table, or interpolated on the graph itself using the constant temperature, pressure, or entropy lines or curves respectively. And these represent, for example, yung different stages kung saan you give off or absorb heat. And we'll look at that in the succeeding slides. Right, so technically yung deviations naman from standard vapor compression cycle are just kung nagkakaroon ka ng superheating or subcooling. So take note, ito kanina yung A nandito siya. Pag yung A prime naman nasa superheated region na siya. Okay? On the other hand, in this case, imbis na nasa saturated liquid state yung liquid mo at point D, naging subcooled siya. So we will not discuss, in reality of course this happens, pero hindi na muna part ng discussion natin yun, as we will stick to the basics, but just to show you that these things could happen. And in theory, they will make your calculations harder. So although we could use the charts no and ruler and paper para solve ng problems, another thing we could do is use the pressure enthalpy tables in the same way we use the steam tables no. So in Singin-Hellman there are appendices for this one, but I think you can also find other stuff online, and actually sa online minsan meron ng mga calculators for this one, even for the steam tables na imbes na mag-interpolate kayo, isusuka na lang nila sa inyo yung values for the certain temperature or pressure you're looking for. So in any problem involving calculations on refrigeration from the vapor compression cycle, meron na talagang steps yan. So depende kung ano yung refrigerant mo, yun yung hahanapin mong table or chart niya. And then we have to find simply the H1, H2, and H3 values, which are essentially the enthalpy values at specific points in the curve. And the simplest way to find the H1 and H2 is to, if conveniently nasa saturated liquid or saturated vapor curve sila, then these are either the HV or HT values for specific temperatures. Now, for example, dito sa condenser, if the condenser temperature is at 30 degrees Celsius, then the enthalpy for saturated liquid at 30 degrees Celsius for that refrigerant would be your H1. On the other hand, para naman sa evaporator temperature mo, yung evaporator temperature mo is at minus 20 degrees. Okay, then H2 would be, in this case, the enthalpy of the saturated vapor at minus 20 degrees. Okay, and then drawing those two horizontal lines, you try to find B as the intersection of the constant entropy curve emanating from point A and intersecting with your horizontal line dB. Okay? So yan, medyo extrapolated na yan pag ganyan. And the answer for each student will be off by maybe plus minus a few units. No? So when we're dealing with refrigeration, one thing of importance is the cooling load or the rate of heat energy removed from a given space. And typically, there is a term we use which is called 1 ton of refrigeration, or in energy terms, it is equivalent to the latent heat of fusion of 1 ton of ice in 1 day. No, ibig sabihin, kung meron kang tubig at 0 degrees Celsius and you have 1,000 kilograms of that, anong rate of heat transfer ang kailangan mo para ma-turn siya into ice at 0 degrees Celsius in 1 day? Or the amount of the rate of energy transfer you need or heat transfer consequently to melt 0 degrees of ice na isang tonelada sa loob ng isang araw. So if you do the math for that based on the heat of fusion of ice for 1,000 kilos divided by the number of seconds in a day, you'd get a value of 3.5168 kilowatts or um, kilojoules per second. Alright, so since makita natin dun sa graph kanina, di ba, yung parang curve dun sa right side is the compression part. And as you can see, when you do compression, there is an increase in entropy. And that increase in entropy actually corresponds to the difference between H3 and H2. Therefore, the work done on the refrigerant during compression is denoted by this equation where M is the mass or mass flow rate of the refrigerant. Okay, and sabi ko nga, typically yung compressor yung pinaka nagko-consume ng power sa ref nyo. Kasi the rest naman halos ilaw-ilaw lang or kung may iba pa silang pump or something or electronics. Pero generally it's this one. Okay, the amount of heat that needs to be rejected to the environment for refrigeration to continue to work is consequently, pag makita nyo dun sa graph, so yun yung point B hanggang point D na line denoted by H3 minus H1. So take note that this is both the heat from the food and the heat from the compression, na parehas mong kailangan iba to palabas ng system mo. Okay, and usually, kung iisipin natin, di ba minsan yung refrigerators, mas hirap sila pag summer. No, kasi in this phase, when you reject heat to the environment, yung temperature gradient na ng condenser temperature niya versus the ambient temperature yung nagtitake into effect. No? So, ibig sabihin, kapag mas malapit yung condenser temperature sa ambient temperature ng surroundings, mas mabagal mag-transfer ng heat and therefore, mas mahirap palamigin yung refrigerant. And that is the reason why mas either hirap na nga si compressor tapos mabagal pa lumamig yung food nyo pag summer versus pag let's say December or January. Alright, so the refrigeration effect is actually denoted by H2 minus H1. So ito yung total amount ng heat na ina-abstract mo mula dun sa pagkain. And this is just to emphasize that again, refrigeration is actually a heat pumping process, no? So yung unlike sa heating wherein yung kuryenteng kinokonsume mo sa electric heater ay kino-convert mo directly into heat, sa cooling, the energy you consume is to operate the heat pump or allow the energy to flow in the reverse direction. So with that being said, we have a term called the coefficient of performance, which is a ratio of the useful refrigeration effect obtained from the system relative to the work used up to produce that effect. So in short, it is the ratio of the amount of heat abstracted from your food versus the amount of energy needed to abstract that heat, which is essentially yung power requirements ng iyong compressor. Okay, and that is simply the ratio of them H2 minus H1 over H3 minus H2. The typical COP value is around 5 or 4, no? So generally you would expect a refrigerator abstracting, let's say, 1 kilowatt of heat to, at a rate of 1 kilowatt rather, to have a compressor that's around 200 watts ang input. So the mass flow rate naman of your refrigerant, so M dot dapat yan may tuldok sa taas, no? Is equal to the Q, or the total heat abstracted, divided by the difference of H2 minus H1. So this would determine how much refrigerant you need to use in a system